I'm Sarah, and today we're going to be figuring out how you can combine Stoich and the ideal gas law. In this problem, we have 1.2 liters of oxygen gas at 1.34 atmospheres of pressure reacting with excess iron to produce iron oxide, which is just rust. The reaction is run at 40 degrees Celsius. How much iron oxide will we produce in moles and grams? So it's pretty clear what we need to find here. We need to find iron oxide in moles and grams. But how do we get there? What do we have? We have some data for oxygen, but we don't have how many moles of oxygen we have. We have the molar mass of iron oxide, so once we find moles, we can convert to grams. And we have R. Now, the presence of R right here tells me we're going to need to use some kind of ideal gas law. Let's figure out first how we can get from oxygen, which is what we're starting with, to iron, which is what we're ending up with. The only way you can convert between two species in one chemical equation is to use stoichiometry. So what we have here is we are going to get 2 moles of iron oxide for every 3 moles of oxygen gas that we put into the reaction. So that is our conversion factor between iron oxide and oxygen. And if you look at our conversion factor, you'll see it's in moles. So we can solve right away for one of the things we need to find, and then using the molar mass we can solve for the other thing. But first we need to get how many moles of oxygen we started out with. Let's look at the data we do have for oxygen. We have volume, 1.2 liters. We have pressure, 1.34 atmospheres. We have temperature, which is 40 degrees Celsius. And if you add 273.15 to that, you're going to get 313.15 Kelvin, which is something we can actually use in a gas equation. And we were also given R right up there. So now we have volume, pressure, temperature, and R, and if you remember the ideal gas law, PV equals nRT, we have everything but N, which is the number of moles, and that is what we're going to solve for. So let's solve this out so that we can put N on a side by itself. We'll divide both sides by RT, and we get PV over RT equals N. I'm going to jump to the next page so that we can fill all of this out. Now you're going to remember volume is 1.2 liters, pressure is 1.34 atmospheres, and temperature is 313.15 Kelvin. R is 0.08206 atmospheres times liters over moles times Kelvin. So let's fill this in. Volume, 1.2 liters, times pressure, 1.34 atmospheres, divided by R, so 0.08206 atmospheres times liters over moles times Kelvin, times 313.15 Kelvin, and that'll give us moles. And if you solve that out, you're going to get 0.063 moles of oxygen. Now let's jump back to the last page and see where we need to go next. We have our conversion factor right here, 2 moles of iron oxide, and we can use that very quickly to get us to moles of iron oxide, which is the first answer that we need. So we have 2 moles of iron oxide per 3 moles of oxygen. We're going to multiply that by our 0.063 moles of oxygen and cancel those two out, leaving us with 0.042 moles of iron oxide. That's the first half of our answer, right? We've gotten one of the things we needed. The last thing that we need is the weight of iron that we produced, and here we have the molar mass of iron oxide, 159.69 grams per mole. 159.69 grams per mole. I'm going to rewrite that so it's actually a fraction. And multiply it by the number of moles that we have, 0.042 moles, to give us 6.66, which we're going to round off to 6.7 grams of iron oxide. And that's the answer to our question.